Welcome to lecture 22. These are the learning objectives of today's lecture. In the previous lecture, we've seen how to derive the Tae-Hyuk's one-dimensional consolidation theory. Today, we're going to learn how to solve the Tae-Hyuk's theory to estimate the excess pore pressure at a given location of interest and at the time of interest. And then we'll identify the degree of consolidation and the difference between this one from the average degree of consolidation. And lastly, we'll see how to estimate the time-dependent settlement in this consolidation analysis. So previously in Tae-Hyuk's consolidation theory, we have derived this equation, round u over round t is equal to CV times second derivative of the excess pore pressure with respect to the depth, since we are looking at the one-dimensional compression. And here the CV is coefficient of consolidation, and which is a function of K, the permeability, and the initial void ratio, and the volume compressibility, AV. So let's look at this configuration here. So we have the clay layer, which have a H0 thickness, and overlying there's a sand layer overlying the clay, and also there's another sand layer underlying it. So these two sand layers at the top and bottom will play as a drainage layer. So water will escape to this sand layer. So then when the delta sigma, the total stress increment, is applied, then the excess pore pressure will increase by what? Delta sigma. So initial excess pore pressure will be the same with the delta sigma over the entire length. And then with time, it's gonna decrease like this. So initially it was like here, delta sigma over the depth. So this is here at the top, and at the bottom, this is at the bottom of the clay layer. And it's gonna decrease like this with time because the water will escape. So then the boundary condition, let's look at the boundary conditions here. The length of the longest drainage path for water to escape is called HDR or H. So in this, you have a top and bottom layers, which is the drainage layer. So then the half of the clay thickness will be the longest drainage path. So it's called the double drain layer system because you have a drainage layer at the top and bottom. So in this case, H will be H0 over 2. So half of the clay thickness. For single drain layer, which is the case that, so this is the clay, and at the bottom could be rock, impermeable rock, and at the top you have a sand layer. So then water will escape to the top sand layer, right? So here also will go. So for the single layer, the longest drainage path length will be the same with the clay thickness. And another boundary condition is the initial condition. When t is 0, so at the beginning, when delta sigma, the total stress increment, is applied, then pore pressure, same with the initial excess pore pressure. The initial excess pore pressure will be the same with the delta sigma for the entire clay depth. So for the depth Z from 0 meter to 2h meter. So here 2h is for the double drain system. So double drain system here. So this is for the entire clay thickness. And the last one is at the time, at Z is 0, and at Z is 2h, which means that the at the interface between the clay and the drainage layer, so here is 0, and here G is 2H. And when time is more than 0, so as time just passes, then pore pressure here is 0 because it is just facing and at contact with the drainage path or the drainage layer. So the water here will not be overpressurized. So there's no excess pore pressure. So lower and upper boundary is the free drainage boundary condition. So for this configuration with this boundary condition, if you solve this partial differential equation, then you can get this exact solution. So here the U is the excess pore pressure. So excess pore pressure at a given location Z, so wherever that you want to find out, right? It could be here or here or here, right? And at a time of interest, it could be a 1 year later or 2 year later or 1 month later. And then this excess pore pressure at a certain time of interest and at a certain location, a certain depth, is a function of initial excess pore pressure and several factors here after that. Here the M is just a coefficient for the Taylor expansion, and there's a Z, small z over H, which is called the depth factor. So capital Z is depth over the drainage path length, the longest drainage path length. So here H is length of the longest drainage path. And there's another term T is the time factor, and here time factor is defined as this equation. So CV times T, small t, over H squared. So H is again is the length of the longest drainage path, and the T is the time in question. So if we draw the excess pore pressure distribution over the length of the clay, over the depth of the clay layer, in the double drain system, so you have 2H, and here's the drainage path, drainage layer. Then excess pore pressure, initially it's gonna be like this, right? So this is by the delta sigma at T is 0. But with time, as soon as the time passes, at the top layer and then at the bottom layer here, the excess pore pressure will be 0. So it will shape like this. And with time, it's gonna dissipate because the water will escape. So it's gonna dissipate like this. So with time, eventually the excess pore pressure will go to approach to 0. In a single drain system, so you have the drainage layer at the top, and at the bottom you have an impermeable layer. Permeable. In this case, the whole clay thickness will be the same with the longest drainage path length. And then initially again it's gonna be the same. Here's the blue one here, and time is 0. And as time passes, at the drainage path, at the top, because it's in contact with its sand layer, the excess pore pressure will go to 0. So it's gonna be like this. So with time increases, excess ball pressure will decrease with this kind of a distribution. Okay, then we can define the degree of consolidation, or it's called also referred to as the consolidation ratio. And consolidation ratio at a depth z is defined as the void ratio, relative void ratio reduction. So E naught is the void ratio before the start of the consolidation, and E1 is the void ratio at the end of consolidation, and E is the void ratio at the time in question. So if the void ratio change, if we draw it, so void ratio will decrease with increase in vertical effective stress like this, then this could be E naught, and here the initial effective stress will be sigma naught prime, and when the initial effective vertical effective stress increase by delta sigma here, then it will decrease to, the void ratio will decrease from E naught to E1, right? Then if the current void ratio is somewhere here, which is E, and then we can define the consolidation ratio by looking at how far this E approaches to the E1. So that's the definition is given here. E naught minus E over E naught minus E1. So if the the current void ratio approaches to E1, then consolidation ratio will become 1. So that's also 100% consolidation ratio, or the degree of consolidation. And 0% is when the E is the same with the E naught. Right? Okay, so the UZ move from, the range of that is from 0 to 1. And if the curve is linear, also we can convert it to convert it to the function of the vertical effective stress. So here initial effective stress is sigma naught prime, and the final effective stress is sigma 1 prime, and this is the current effective stress, sigma prime. So sigma prime, here, let me use, so this should be the prime, sigma prime minus sigma naught prime over sigma 1 prime minus sigma naught prime. This is the delta sigma, so which is the total stress increment. So then if we use the total stress and the pore water pressure concept here, then we can convert it to the excess pore pressure. So the pore water pressure here, UZ, the degree of consolidation, UZ, the capital UZ, is 1 minus U over UI. Here the UI is the initial excess pore pressure, and U is the excess pore pressure remaining at the time in question. So then we can solve this equation using this analytical solution here. So U is the excess pore pressure at the time in question T. So then if we plug it here, then you get this equation. And here you can see that the UI is cancelled out because of that we divided here. So the degree of consolidation is not dependent, it's independent from the initial excess pore pressure. So no matter how large the initial excess pore pressure is, doesn't affect the degree of consolidation. And also you can plot this equation in a kind of for a given for varying the depth z and not for the different t, time factor t. So then it's called the isochrone curve, and you can draw it. In a square, and the x-axis is the capital UZ, which is degree of consolidation, and y-axis is the depth factor, capital Z, which is the same with small z over h, and this ranges from 0 to 2 for the double joint system, right? So this will be the bottom of the clay layer, and this will be the top of the clay layer, and at the center the depth factor will be 1. And then the isochrone curve will shape like this symmetrically, and as time factor increases, which means as time goes by, the UZ will increase and it will approach to the value 1. For example, when the time factor, let's say this is the time factor, time factor is 0.9, and when the time factor is 0.9, then at the center of the clay layer, UZ, the degree of consolidation is 0.86. So then at the, for a clay layer, when the time factor is 0.9, at the center, the pore pressure, 86% of the initial pore pressure has been dissipated. And this figure is more accurately drawn in the textbook, and also you can find the copy of it in the next page here. So if you can calculate the time factor t here, according to the definition, t is CV times small t over h squared. If you know the time factor, and if you have a certain depth of interest that you want to find out, for example, maybe quarter depth or the half, the midpoint, or the 3/4 depth, then you can find the consolidation ratio or degree of consolidation UZ, and from that you can identify how much the consolidation process has been completed. Okay, then so the degree of consolidation, the capital UZ, varies with depth from this curve. You can find out, right? And the definition is 1 minus u over ui, and this is function of depth factor and time factor t, right? So when you ask the degree of consolidation, you have to specify the what depth that you're interested in. Is it a quarter depth, 25% from the top, or the 50% or 75% from the top, right? So then it would be kind of difficult to represent the whole clay layer. So then can we get an average degree of consolidation that can represent the whole layer thickness? So people have developed and suggested the parameter called the average degree of consolidation. And here we use the UAVG, or just U. So for a given T, we know that from the consolidation ratio equation, This is UZ, 0 to 1, and this is depth vector 0 to 2. Then the curve will look like this. And then this area indicates the completeness of the degree of consolidation or consolidation procedure. So when UZ is 1 for whole layer, it will be like here, right? So then in the case, it's gonna be whole rectangle here. So then by area integration, we can define the UAVG, so average degree of consolidation. So the area that has been completed divided by the area when the whole layer consolidation of the entire layer is completed. So then this so here the height is 2h, right? And from here to here is just 1. So then this equation will eliminate the factor, the depth vector. So then it becomes just a function of the time factor t. And the result is shown in the below here. So this is the final equation for the UAVG. And you can see that the equation doesn't have the factor z, right? The parameter. So you only have the time factor t. So function of time factor t and no effect of z. So then also you can find out the graph, the plotting this equation, which is this one. So with an increase in time factor t, UAVG also increases non-linearly. And this is a kind of complex equation to use, right? So you have to have some computer to accurately estimate it. So for practically, there's some approximation. So then for when the UAVG is less than certain point, then you can use the here when the UAVG is less than 60%, then the square root of time factor t shows a linear relationship with the UAVG. When the degree of UAVG, the average degree of consolidation, is more than 60%, then the power relation is shown with the UAVG. So the people have derived, kind of suggested the approximate solution as follows. So when the UAVG is less than 60%, so when the degree of consolidation average value of that is less than 60%, then you can use this one. And UAVG is more than 60%. This equation. So depending where it belongs to, you can use the first one or the second one to estimate the time factor t. or if you know the time factor t, you can use either one to get the UAVG. Okay. So then the last one is the settlement estimation. So actually the settlement is related to the average degree of consolidation. So the UAVG is also can be defined as the settlement at the time in question as t over the ultimate primary consolidation settlement. So do you remember this equation, right? This equation, the SC is you can get the settlement consolidation settlement in the clay using the CR and the initial effective stress and the final effective stress and the pre-consolidation stress and the CC and the void ratio, etc. Right? And this is the ultimate primary consolidation settlement. This will be the SC here. And if you know so let's say that the 10 centimeter is destined to occur and 8 centimeter has occurred so far, then 80% will be the average degree of consolidation. Okay, so in the class, we're gonna see how to use this average degree of consolidation and estimate it, and also the degree of consolidation using this isochrone curves. Okay, that will be it for this lecture. Thank you.